Okay, so I think we are live now. We are going to begin the discussion on week 7 today, which is about symbolic testing. A slight difference from the other techniques that we have seen. So something new that we are going to see now. Okay, is the screen visible?
Yes, sir.
Okay, so week 7. Let us see if that is coming up slightly slow today. Okay, so idea in symbolic testing is that, see, what we have been doing so far is we are having a program, okay, and we are trying to give inputs, okay, to exercise the various possibilities or execution paths that are there, right? And some test inputs may go into certain portion of the program while others may go into other portion and so on and so forth. It may be that if you're going one sort of input, like one category of input, then you are getting your the program is going into the same branch per se. Let's say we have a similar set of integers. Think about integers, right? So we're always giving one kind of integer. Let's say so some condition is there, right? So if the input belongs to one category, then the program also behaves the same way essentially. That's what happens, right? So we needed a way to figure out, and this is some sort of automation also. We're trying to do automation in testing also. So this is the very first step that we are going to see some sort of automation that we can implement in terms of testing. So in this one, we are going to see how to drive the program, in the sense that so you have multiple possibilities for the execution paths, right? So you have branching statements. So if one case you go to the if case, maybe the other case you want to go to the else branch and so on. So right, so you want to drive the program that way. So essentially, the idea in symbolic testing is something similar. Okay, so as we move along, I think the best way to understand this is by example. So we'll just give a little bit of background and then go to examples. I think it'll be easier to understand that way. Okay, so essentially, it says symbolic execution means finalizing given program to determine what inputs cause each part of the program to execute. Meaning, you know, inputs so that they are going into different parts of the program, not as if you're giving only one kind of input which is always exercising one part of the program, right? Because the idea in testing is to as thoroughly as possible you try to execute the program, right? So as to uncover bugs or errors or faults that are there, right? So idea is that you want to go to different portions, that is right. And in complex programs and very large programs, the number of possibilities that are there are very huge, that could be there, right? So you want to try drive the program some sort of automated fashion. So that is the idea. Okay, exercising different execution paths. Different execution paths meaning the various from the starting node, from the initial node, what kind of other possibilities are there, right? What kind of paths you can follow and so on and so forth. Okay, so that's what we're going to see. And the other thing in symbolic testing is execution is that it is also allowing us to solve the reachability problem, right? How do you reach? We discussed about that briefly in one of the earlier sessions, right? How do you reach a portion, right? So let's say you wish to test a particular method or a particular logic within that method. Then you will first of all have to reach it in terms of the initial input that you give, right? So in the program there's this initial input that you give, and the program behaves in a certain way, and then it reaches a certain place, right? So that's what happens. So we are trying to then figure out how to do that, like in an automated fashion. Okay, so that's the idea. We'll go forward and see an example. So idea is that, consider this. Okay, we have a sum. So symbolic execution, what happens we have to contrast this with the normal execution, meaning the concrete. We also call it the concrete execution, okay? Because the inputs here are concrete, meaning it's some sort of actual input that is given, right? 135. So if we give that, what happens to the state of the program, right? So we are trying to encapsulate that here. We're trying to represent it here, right? So after statement one, we don't have XYZ defined because remember we are talking about this, okay? So, and then we have XYZ is blank. ABC is started at 135 because that's what it goes as the input for the sum. Okay. Now after statement 2, X becomes 4. Why? Because you follow essentially you follow the program, right? Whatever happens, you also are doing it on the inputs accordingly and figuring out what the states would be, right? So at the end of the day, at the end of the execution for that particular method, you get the result, which is 9 in this case. Note that the dashes represent the unchanged values, right? So after statement 1, if B is 3, then it is not changed in statement 2. And in C, you have all ABC remains constant, but X, Y, Z are changing, right? And before, let's say mm, before initialization, those were not available, therefore question mark, right? uninitialized value. So that is the idea in concrete execution. Like you're going to get a value, right? That's what happens. Now, in the case of symbolic, just a second. So in the case of symbolic execution, what happens is instead of having actual values, we are going to provide a symbolic representation, symbolic variable, that is, okay, symbolic representation for the variable. And as we move along, we are going to formulate path constraints, or in some sense it's a symbolic representation of what is happening, right? So you have, let's say for a alpha 0, alpha 1, alpha 2, or something like that. Then essentially instead of a and b, you're going to have a formula which represents x, right, and so on. Instead of having this kind of value, you're going to have something like this. So you have for a b c, instead of putting actual values, now we have alpha 1, alpha 2, alpha 3, and as we follow along the program, we are creating these expressions. Okay, so this will become our path constraints. Okay, which can be used to then figure out how to drive the program into different branches and so on. Okay, so this is called PC, which is path condition or constraint. Okay, so this, I understand that this in the beginning it might not be very apparent as to what we're going to do with this, but as we move along, it will become clear. Notice that when we start, the path condition is assumed to be true because we have to start, right? We have to proceed. So if it is false, idea in path condition is that if the path condition is true, then you're going to follow that path. Think of it like if case, no? If it is true, then you're going to follow, right? So if in the beginning itself, in the first statement, the path condition is false, then we cannot proceed, right? So to begin, to start, you have to have the path condition is true. Now, depending on what other statements are there and so on, the path condition may vary. So we'll see that in this particular example. Okay, so this is some sort of involved program, not very involved, but just to get the point across. So essentially we have the int main from where we start, and we are interested in testing the test me method here. Okay, so test me takes two arguments, integer x, integer y, and z, and so all these functions are happening over that. So the idea is, in terms of the initial input that you provide, we are going to create path constraints. How do we do that? So you have x and y. Okay, now z becomes twice of y. Okay, so we are going to write it like that only. You see? So in this case, we have twice of y equal to x, because this represents the first condition, right? So what we are doing is we are trying to write everything in you know with respect to the initial inputs that we are given. Okay, some symbolic variable is there. Let's say alpha 0, and as x moves along in this program, in this particular method, then you are going to follow along and accordingly write the expression for x and so on. Right, so x becomes x naught, and then you follow. So for example, for y, what happens is you have y, so z becomes twice of y. So twice of y, so the value of y goes here. So let's say y naught. So y naught goes here, it returns 2 into y naught. Okay, and it comes back and so on. So you have the if condition becomes what? 2 y naught equal to equal to x naught, right? That's what the condition. The first one is. The second one is accordingly you have x naught greater than y naught plus 10 and so on. So this so essentially the idea is we get this kind of a predicate, okay, or a path condition, right? So I'm sorry, I think this is x naught. X naught greater than y naught plus 10 is the expression here. Okay, so you get this. Now, idea is that if we have this kind of a condition, because I can follow along, right, the program, and then accordingly create expressions like this. If I'm able to solve it, meaning what does it mean to solve this predicate? Meaning, if you solve this path condition, it will give you values for x naught and y naught, whatever inputs may be there. So that if you put those values, this entire expression will turn out to be true. It becomes true. Solving means you get a solution, so that we put back that solution into the x naught, y naught, so that when it happens, like it is true. So if it is true, then you are going to follow, right? That's what it means to solve this particular thing. Okay, so idea is that we can do something like that. We have the first expression for this which one, for the for this condition, right, at 6, line number 6, we have x, if z is equal to x, so that's what we have. And so if it is false, then we are going to, so idea is that if you have this kind of a input, then it is going to be false. That's how you read it. This is a symbolic execution tree. Okay, now if it is true, so notice that if it is false, then there is nothing else to check, right? But if it is true, then we get another condition, right? So to solve this, essentially there are two possibilities. If you want to get it false, like the next one, the next condition, you want to make it false, then you can put this input. So idea with this approach is that the input that you got after solving the predicates, and how we'll understand how to solve the path constraints. So once we solve it, now if we put it back as an input, initial input, then the program is guaranteed to follow the exact same path. Okay, So if you put, for example, x is equal to 30, y equal to 15, then the first condition will become true and the next condition will become true. Okay. If you put 2 and 1 respectively for x and y, then the first condition becomes true, the second condition becomes false, and so on. So that is the idea. Is that clear up until this point? Any questions on this?
No, sir.
Okay, very good. So that's the idea. So essentially, yeah. So one more thing is the interesting point is to assume that we somehow know that there is an error here, or we want to just test if there is an error or there isn't an error at line number 8. Now, idea is that in such a deeply nested structure, and this is not deeply nested, but in general, you can think about it. No, it's a large program, so many conditions, and so on. So you want to reach a particular stage. No, so that is what reachability is about. So I want to test in this case, but then again, you have to first of all reach it, then you do your input and so on. So idea is, but then again, the inputs are getting transformed in between. No, so the thing that you provide initially may not be the same thing that leads you to here and at number 8, right? So the idea is that with respect to wherever you want to go, right, the symbolic path conditions can actually give you values in terms of the original input. So you may not know that there is a 2 into v going on there, right? And but you just provide input here. So to be able to reach number 8, you will have to get values such that those conditions are true, and then only you get here, right? So this helps with reachability that way, because this gives you values in your initial, with respect to your initial variables that are there. So that is the nice part. Once we get it, you just put it back and you're going to get it to follow the same path. And therefore, so in this case, if x is equal to 30, y equal to 15, you get an error. So that is how it solves it. So idea is that this is one way, right? Because you are just kind of following the program in a symbolic fashion and trying to solve the predicates and getting the test cases. So this is like test inputs you're getting, right, from it. But the idea is, so this is some sort of program proving also. So the idea is that in program proving, we say that we are going to mathematically prove the program is correct, right? Now, this is not possible actually, because there are so many various, so many cases, right? So it is not practically possible to actually prove it mathematically, rigorously prove that the program is going to be correct in all cases, right? So that is not practically feasible. On the other hand, what we do is we provide test cases, right? And that have there its own shortcoming, because sometimes what may happen is you're not testing for all cases. All meaning, reasonably good set of test cases. How do you define that? Because maybe you are testing for a specific category of test cases, but you are missing out on other possibilities on the program, right? So you don't know. Like, you have to balance it. You cannot prove it, but also if you just have test cases, then you are not sure as to what extent it is covering and not covering, and test cases are not exhaustive also, right? So working on the program other inputs, meaning whatever inputs are given in the test case, are tested. But what about those which are not there, right? So that's the idea. But proving says that I'm going to go, not going to use test cases. I'll just prove it. But this is practically not possible, right? Because it involves formal methods and all other sorts of things. We're not going to go into that detail of that much for now. So that is what testing says, that we are going to just provide inputs, and if it works on those inputs, it is okay. Proving on the other hand says that I'm going to just rigorously prove that everything is correct. That is not the case, then I would not say the program is correct. So essentially, these are two extreme alternatives. That's what happens. Okay. Now, so the idea is that basically, because this is not practically feasible to do program proving, and testing also has its own shortcoming. So symbolic execution is actually a practical approach between the two extremes. Okay, we are still doing testing, but it's just that some parts of the program will drive automatically. Will drive it and get test cases out of that. Such cases, right? Wherein you have formulas and mathematical things involved, not necessarily mathematical. It could be anything, but idea is that such cases you want to test specific logic. Still, you're not doing the program proving in its entirety, because that's not possible to do it for the complete source code. But some places you may do that, no? So that's what symbolic execution helps you with. Idea is that if you are able to uh, just a second, is a yeah. So if you are able to solve for the symbolic path constraints and give that input, no, actually each symbolic execution is equivalent to a large number of normal test cases. That is the key part. Okay. Idea is that, so for example, if I am able to get into this branch, this node, and somehow I'm able to do the true and true case for these two conditions, path constraints, then it means that I have checked for all such cases wherein these two conditions will become true. You understand? I mean, this input doesn't need to be this one, but any one input from that particular case, if it is exercised, then it is sufficient for all other inputs that may lead to the same path. You see, because x is equal to 30 and y is equal to 15 is not the only input which will lead to this case, true and true. There might be other inputs also, but if we have tested for this one only, no, symbolically, then I'm sure that I need not test for the other cases. Then I'll go to the other branch. Then you see, I'll not test for the other inputs that lead to the same case again, same execution path. That is, this is what execution path is. Okay, so if I've tested for this execution path, then I may just go to the other execution path, and I need not test for equivalent inputs that way. You understand? Equivalent in the sense that we provide the other input, but it'll lead to the same execution path. So that's the idea. We're trying to drive the program. And again, the inputs may be very different. You see, x is equal to 30, y equal to 15 is leading us here. But again, we don't know exactly what change will we make to this x is equal to 30 so that we get to the other branch, right? We don't know. So that's what symbolic execution is helping us with. Okay, it'll allow us to solve it and do some automation that way. Okay. So yeah, that is okay. Yeah, we instead of putting a sample input, we are kind of symbolically doing for a set of inputs. Set of inputs, how? Because everything that will satisfy those path conditions will eventually fall into the same branch or execution path. You see, so that's how if you test for one, you test for most of them. I mean, all of them essentially, all equivalent cases. That is okay. Now this is okay. Now some discussion about the how you know the symbolic execution itself works. The idea is that PC is initialized to true, meaning we want to move forward, right? So therefore it is true to start with. Now, if you hit a conditional statement, remember again, a program is a linear thing. Every path is linear unless there are conditions, right? If there are no if conditions or no loops or nothing like that, there's no conditional statement. Then in that case, it becomes a linear thing, and there's no point in having symbolic execution there because there are no possibilities, right? You just have a linear thing. You can just execute one way. There's only one execution path possible. However, once you have conditions, then the possibilities are growing exponentially. Eventually it'll start growing exponentially, and depending on how many other conditions you have and loops and so on. So idea is that the symbolic execution is only concerned about the conditional, because that's where your decision statements will come and so on, right? When you are going to take the then branch or the else branch and so on, that's where the condition is. So essentially, it works with that. So we start with true now. If an expression is there in the if statement like this, so if e then s1 else s2, that's okay. PC is updated to. So as soon as we hit a particular if statement, then it is and we do and you know so and we give the expression essentially to whatever is the current path condition and the new if condition that is there, right? Then and a fresh path constraints PC prime, which is the negation. So what happens in symbolic execution, you have to remember this, that when we hit a if statement, a conditional statement, we have to essentially create two path conditions, one for the then branch, the other is the negation of that else case. Okay, it creates two of them. Now it checks if PC or PC prime, either of them, either the true case or the false case, is satisfiable for some assignment of concrete to symbolic values. That is, some concrete solution exists for that. It might be that's a contradiction or something like that. You might not be able to solve it and so on. And some discussion about that will go and discuss that moving forward. How to solve, like what does it involve to solve it and so on. Idea is that if it is solvable, meaning there's some concrete value that you can put back and get that condition, uh, evaluating to true or the other case, the false. I mean, essentially the not of that expression, if that not is true, then that is the false case, right? So essentially we have to solve it that way. So then you go to the then branch, otherwise you go to the else branch. That is the idea. So essentially what happens is, unlike concrete execution, both the branches can be taken, resulting in two execution paths. Because in this case, concrete execution is only going to one case, right? So if you have a concrete set of values, then it is going to either go to the then branch or the else branch. It cannot go to both, right? But symbolic, what it does, it generates path conditions for both cases and solves them, and it drives the program in both branches. Okay. So that is what the idea is. Now, if any of the path, and we keep doing this like that, if any of the path condition or path condition prime, which is the negation, is not satisfiable, then on that path we terminate. Okay. So the key point here is, in concrete, rather in symbolic execution, we'll have two path constraints for every if condition. Okay, meaning the true case and the false case. Okay. Then again, so once you get that PC, the expression, you have to use a solver to solve it. Okay. So we'll discuss about the solver also. Mm, yeah. This is okay. Now, yeah, exactly. We solve that PC to get the concrete input values. This is okay. Yeah, and symbolic execution can be terminated if the program hits an error. Like if it exists there's some error, uh, then it stops. That's okay. Yeah, if the program executed on on these concrete input values, which are taken from by solving it, no, by solving the path condition, it will take exactly the same path as the symbolic execution, terminated in the same way. That is the key point. Okay. Yeah, these concrete inputs ensure that coverage is achieved in testing by taking different execution paths in the program. That way, we drive the program into different cases. Okay. Now, so essentially, we start with like a sigma is representing the state, your state, no, whatever is assigned to. So x is, let's say we assign a symbolic value x naught to x and y naught to y, and then so we keep on going forward, and then so what happens with y is the z becomes 2 of y naught, right? So because this method got executed at this point, that is equal to twice of y. So the symbolic state got updated with this, right? And so on. So we keep maintaining this. And line number 6, what happens here? Line number 6, there are two possibilities, right? Either z equal to x or not equal to x, right? So two path conditions will be generated accordingly. You have x not equal to, again, remember, all of this is in terms of the initial input, x naught and y naught, everything. Okay, there are no intermediate variables or anything like that. We have initial variables which are putting, and accordingly we are writing in terms of that only. Because x not equal to 2 of y, 2 y naught, and then x not equal to 2 y naught, two cases. And then we are having this kind of a situation. We solve it. How do we get 3 here? One case is the first one becomes true. So if one case is first one becomes false, let's say, so that is the false case for first one. Second, if this first one becomes true, then immediately we hit another if condition, right? So the first one becomes true and the second one becomes true. That is case number 2. Case number 3 is the first one becomes true and the second one becomes false. That's why 3 cases, okay? Because if it is false, the first one, the outer if, number 6, then you're not going to have a, you don't, you're not going to check for what is here in number 7, right? That's what. So uh, therefore you only have 3 cases, right? So these are the 3 concrete inputs, okay? And how did we get from the path condition? So that we'll talk about. Okay. Now one more notation you have to remember is regarding loops. What to do regarding loops? How do you do symbolic execution with loops? Okay, and the code could be anything. Code could be given, and then you have to figure out the correct representation or correct path constraint for that. So idea is essentially it will be something like that. Okay. So we say and this is a logical and. Okay, and over I belonging to I1 to n, right? Ni greater than 0 and n, n plus 1 less than equal to 0. What happens essentially is we are going to ask for a loop with a sequence of n truths followed by a false. Why? Because if we keep giving true, for example, for this while loop or any other loop which may be given in the code, right? So idea is that we'll keep going forever. How do we terminate then? How do we move forward with the program? We have to have a false case also. No? It's like, let's say, so we constrain it. We say that, okay, we are going to follow it 5 times. And then the sixth time, the sixth time it is false. So we exit from the loop. So that is what it is saying. It is saying PC for the loop is a sequence of n truths, meaning n times we are going to follow. N times we are going to go inside the loop, followed by a false at the last time. So essentially, 1 to n, how many numbers are there? N numbers are there. No? So n times we need ni such that it is greater than 0, right? And for the last time, we have a negation. So essentially, this condition is taken from here. Whatever the loop says, no, you're going to put that condition. So this is the true case. We will go inside the loop when n equal to, n greater than 0, right? Or n less than equal to 0, it will become false and will exit from the loop, right? So the negation of that is the last. The last condition is the negation of the true case, essentially. Okay. Is this part clear? Is this notation okay? Any questions on this?
Sir, can you explain one more time this expression?
Okay. This one, yeah. So idea is
Yeah.
you have summation, right? Summation in mathematics, like this one, right? Summation. So this is and over. You are doing multiple times and. Okay. So we can expand it out. We can say ni. So let's say n1, n1 greater than 0 and n2 greater than 0 and n3 greater than 0. So essentially, what is happening? You see this n is a symbolic input. Each time we are taking it, right? So first time we take it, we check n
Okay.
greater than 0 or not. Okay. Then we go inside. If it is greater, then we sum. Again, we are going to get symbolic input. So this becomes n2. So let's say this one is n1. So n1 has to be greater than 0. Then only we go inside, right? First time. So then we do
Yes.
whatever we are going to do in that loop. It could be anything. In this case, it is summing, but it could be product. It could be anything. We do that. Then at the end of the loop, meaning at the end of the iteration, we are going to again take an input. So this becomes n2 then. Okay. Then we check again. Is n2 greater than 0? If it is not, then we exit. If it is, then we go forward. Now my question is different. So this is how it works. This is the working of this particular notation or this particular program. Idea is we are going to ask, I want to go, let's say n times. Okay, let's say I want to go a small n times. Let's say I want to go 10 times, right? So I'll say I want a condition, a path condition. What will be the path condition such that I go 10 times in the loop, and the 11th time, the 11th time I exit. You see? So, so that is what it is. So we are saying for the ni, for the first ni, it has to be greater than zero. For the second ni, it has to be greater than zero. For the third ni, it has to be greater than zero. Let's say I want to go 5 times, right? So the fourth ni, I have to, greater than zero, and then n5 is also greater than zero, so that 5 times the loop is followed. Now for the sixth time, n plus one, the last piece. So that becomes the negation of however I go inside. So for going inside, it has to be greater than zero. No. So what is the not of this? Not greater than is less than equal to zero, right? So not we are applying not on that. Whatever condition is here, no, it will be not of that. Like you apply not uh, to get the other case. Okay. So essentially this. So we have the
So,
sixth time
sir,
is false. Go ahead, please.
here I represent a number of time condition is true.
Yeah, number of time conditions true. Yes.
Okay.
No, not the I, the n actually. The small n you are saying, no? This one.
No,
I
I is
belonging to
element of one and
1 to n. 1n
yes.
is the interval, no? It's, inclusive. So how many numbers are there? So if we have 1 comma 5, then I will be 1 in one case, I will be 2, I will be 3, I will be 4, I will be 5, and so on, and so on. So it's the last time you want to have this. So this is just an expression so that you could follow n times. This is the expression. Okay. Now the code may change. The code may change, the condition may change. We may ask you what is the, again same thing, question may be same, but the expression may change, okay, depending on what the
Okay.
code is. So we may say I want to go, let's say, n rows or n times. It will be a variable. Generally we don't ask for a fixed number. We don't say we want to go 5 times or something like that. We'll say n times we want to go, or any variable it could be. And then accordingly you have to select the correct expression. That is all there is to it. Okay. Like what is the correct expression so that you follow n times. Okay. Now the thing to be careful about is if I say 0 to n, how many numbers will be there? Let's say 0 to 5, how many numbers are there? 6 numbers are there, no? So that way you have to be
Yes.
careful. Yeah. So if there are 6 numbers in this interval, the idea is that, see, idea is very simple. Idea is how many ever numbers you have in that interval, that many times ni is going to be greater than true, right? So that many times it is true. So that many times you're going to have, like you're going to follow that loop, right? So n is true that many times. So you have to be careful about the interval actually. If it is 0 to n, then actually there are n plus 1 numbers. So n plus 1
Yes.
times it will be true. Okay. So you have to be careful. So
Okay.
if it is 0, then the end point of that interval should be what? N minus 1, right? Then again, so 0 to n minus 1, you have n numbers that way. And so accordingly, you have to adjust this one also. So if it is 0 to n, rather the interval becomes 0 to n minus 1. So then the nth n, that is like the capital N and small, how do you put it, right? Both are same. So essentially I'm talking about the small n here. Okay. So the small n is there, just the small n itself, the nth symbolic input for that variable is the negation, right? So accordingly you adjust it. Essentially you have to adjust the interval accordingly. I mean not the interval, because basically it will be MCQ. Okay. And different intervals should be given. You have to select the correct one according to whatever the statement is. Okay. So generally we ask for this one only, right? N truths. Okay. And remember, you have to have the false case also at the end, because if you don't have the false case, then you keep on going infinite times. Like you have to exit, no? Exit from the loop.
Yes, sir.
So that is one kind of question we ask for the expression. The other thing, disregarding this one, the other thing is this. See, remember, we are keeping track of everything, no? Keeping track of the sigma stores the track of what contains what at what point, right? Each point it is changing. If you remember from the above one, you had, so to start with x was x naught, y was y naught. Now at the moment I hit z is equal to twice of y naught, we added a new mapping here saying z is mapped to twice of y naught, because that's what happened in the code, right? Twice of y naught here. At this moment, the symbolic state got updated, right? And so on. We keep on updating it. So now in this case, we're asking at the end of the execution. So let's say I have done it 10 times. That is okay. Now at the end of the execution, what should be the state then? Because again, remember, you have to think about it in this terms, in this in terms of the code that is given. Okay, so number 5 we are summing it up, right? So let's say 5 times I'm going inside. So n1, n2, n3, n4, n5, we are going to sum it up, right? So it will all sum up n times. So some variable will be holding that value, no, the last value with which we exited, finally, the complete sum, how many ever times it
Yes.
was there. And one more thing you have to remember is sum is having the only the ni, right, from 1 to n, but n is holding the last value, n plus 1, not the n. It is because the last time also we checked, no. So let's say 5 times it is done. 5 times I have summed it up. Now for the sixth time, it is going to be again checked, right? So 6 times for the sixth time I take the sixth value for n. Okay. Now I check it. It turns out to be less than 0 or it is 0. So I exit. But the value for n at that moment will hold the sixth value, not the fifth one. Okay. So you have to be careful about the boundary case. Okay. So essentially,
Okay.
n at the end of the execution is the last, not the true case, but for the last one with which we exited essentially. This one, we exited with this n plus 1. So that's what it is holding at the end of the execution, right? But the sum only happened to the extent we got inside the loop, right? I mean, how many ever times we got. So let's say 5 times we got inside. So this is holding up until that only. It is not 1 comma n plus 1. Okay. It's 1 comma n, whereas the actual value of n at the end of the execution is n plus 1. So that is a subtle difference that you have to be.
So some represent a number of times some variable call by function, right? In
Yeah,
while
yeah.
loop.
How many? Yeah, in while loop. Yes, this one. Yeah.
Yes,
How many
yes.
ever times we accumulated? So it could be product also. Accordingly, you change the expression. Meaning, the product symbol, right? The how do you put it? It looks like a Roman numeral 2 actually, like that. It's a product. Some is
Oh
like this
yes.
product. Yeah, that one. Yeah. So if it is a product, then you accordingly select it.
Okay.
Yeah, yeah. Two lines. Two vertical lines that are.
Yes, yes. Just like pi.
Yeah, yeah. Just like pi, correct.
Yeah.
You have, yeah, in general. Yeah, exactly. Same thing. Whatever I explained. It says, I mean, if we don't put a condition, if we don't put a limit, no, we can keep on going how many. So we have to terminate. So therefore, we always say like this: n number of times I want to go inside. It's a reasonable thing to think about, right? Okay, let's say even in prime path, you have this, no, 2 times we follow the loop like that, 3 times we follow the loop, and then after that we exit. Test paths iterate like that. So accordingly, you fix a number. Let's say I want to go 3 times, and the fourth time I'll exit. Right? Fourth time will be false. So that is what it is saying. We have to put a limit on the search. Okay, now this is okay. What else? Yeah, now we'll come to condition the solving of that. So these conditions we are getting, right. That's okay. We are getting all this if expressions, path conditions like this. No, this not this this one. So x not equal to 2 y not, x not equal to 2 y not. No, this Boolean condition predicates, right. So how do we solve them? Idea is again, there is a satisfiability problem in general in computer science, which is NP complete. For those of you who know, coming from DSA, PDSA might know what NP complete problems are. So there is a three-stat problem, which is NP complete. The idea is that essentially self-satisfiability problem is hard for even for computers to solve. Okay, so that is a general thing that we understand. But even with that, even being NP complete, there are good solvers available, constraint solvers, which work with a very huge number of variables actually these days. Okay, and can solve them in a reasonable number of time. Sorry, reasonable. Yeah, in a reasonable time essentially, because you cannot keep waiting for it to be solved, right? So you have to do it fast also. But this problem in general is hard, even for computers. So there's some constraints that you have to go by. But idea is that they can handle, like these days, modern constraint solvers can handle good number of variables and so on. So they can do our work. Practical purposes. How do they do that? Using some heuristics. See, theoretically, the satisfiability problem is hard, right? To get a polynomial time algorithm for this is difficult, right? This is non-deterministic polynomial actually. Therefore, NP complete. So therefore, it is exponential. That is like the number of possibilities are exponential, and therefore it takes a huge number of like it's a lots of time it takes to solve it essentially in general. But what constraint solvers do is they employ certain heuristics, uh, clever ideas with which they cut down the search space and do it faster. For practical purposes, I think most of it will work. They work, but theoretically it is hard to do. Yeah. That is the idea. But for testing purposes, it works essentially. So yeah, so that is the only problem for constraint propositional logic, which is Boolean algebra essentially. Propositional logic is NP complete. That is okay. What else is there? Yeah, so there are two problems now with our symbolic execution approach. One is, see, there are two kind of things. Okay, one is that the the symbolic condition that is there cannot be solved, meaning it cannot be solved efficiently, meaning maybe it's a huge involving huge number of clauses and literals. So even for constraint solvers, it is becoming difficult to solve. That is one case, right? Because of which we cannot do. So this is one of the drawbacks of symbolic execution. But note that when we say cannot be solved, it might also mean that the condition is a contradiction. Meaning we say 2 is not prime, so it is always false, something like that, right? X not equal to X. So this is like a contradiction. So in that cases, it will say that it's a contradiction. It cannot be solved, meaning the formula cannot be solved. We don't get a satisfactory solution for this one. Like for example, for anything, right? Let's say I say X not equal to X naught, right? So this will contradict and cannot be solved. So that is one case when we say cannot be solved. So this is okay. That case is okay because it will report to us. It will say that that is a contradiction and we cannot proceed. Like it will always be false or something like that. So it is solved. That way it is solved. Meaning we say that it is unsolvable or unsatisfiable. So that we'll consider as a solution. Meaning we know that it cannot be satisfied. Right? In case of contradiction like this, like X not equal to X not equal to X naught, like something like that. Some other contradiction might be there. So that is one case. The other case is that maybe there is a solution, maybe there is not a solution, but it is taking a long time to solve actually for the solver because of the NP complete nature of the satisfiability problem, right? It is taking a long time, so you don't know whether it can be solved or it cannot be solved, right? It is just taking a long time. So then if we cannot solve the PC, right, then we cannot get the concrete test inputs. Remember, how did we get that 15, 30 and all that? All these three cases are there. No? So this came after solving the. So we take this condition, put it to a constraint solver, whatever it gives, we just put it. So that becomes the solution for this one, first one. Whatever it gives becomes the input essentially. So if this cannot be solved, assume for some reason, right? Then we cannot get the concrete test inputs, and if we cannot get the concrete test inputs, we cannot test. We cannot proceed with program testing. Okay. So that is one of the disadvantages of symbolic execution. Okay. So yeah, this is key disadvantage. There might be questions on this. Okay, so be careful with this. So it says, yeah, cannot be solved by any constraint solver. Okay. Now other disadvantage, which is even more practical these days, is the underlying program uses functions whose code is not available. So think about client server systems. You have websites and web applications. So the entire code is not on one machine, right? It's going to call something else, and then so how do you get the condition then? Like we are completely executing symbolically, but if we don't have the symbols with us, meaning the code itself is not there, how do we know what conditions are there? Like what is the server going to respond with? In that case, also we'll be stuck, right? How do we proceed? Right? Because we don't have the path condition because the code is not there. Code is somewhere else. Maybe we are calling an API, right? So what the API is doing, we don't know, right? So then again, how do we proceed? So that is another disadvantage. This is also a disadvantage. Okay, that real life programs in general, like huge programs, very huge. Think of web browsers or the likes, operating systems. Okay, very huge programs. So it can have huge number of program paths also, of course. So exhaustively exploring all paths is not possible, of course, because a very large tree cannot be done. Like large in the sense like absolutely huge. Okay, like that. So not possible because exponential number of possibilities again come, right? So but the second one, this one, right? The first one we cannot help it because if it cannot be solved, then it's NP complete problem. This one also, it is kind of, we cannot do anything about it. I mean, we can't do much about it at least. But there are again some limits or some things that you can put, right? So you put limit on the depth of search and so on, so that you exit early. You don't do exhaustive checking. But the second one can be we can do something about this. Okay, so that is what the next discussion is about going to be about, right? Concolic testing. Okay. So the other one, maybe we can continue this one today, or uh, we'll take this up in the next one. Idea is in concolic testing, I'll just give you a brief, is that it does a combination of both concrete plus symbolic. So symbolic, what it was doing, it is doing completely symbolically, right? So if something is not there, let's say I'm calling an API, but the API's code is not there, right? So we have to wait for that the server to return something, and then we can continue, right? So that is the key idea essentially. So what concolic is doing, whatever is possible to do symbolically, it does symbolically. But wherever it is not possible to do symbolic testing, it does concrete. It puts random concrete inputs there essentially, and there's some ideas to that also. Okay, so it does both. Therefore, concrete plus symbolic. That is okay. So that this one maybe we can discuss in the next one. Yeah, it works similar, but the idea of key distinction is that it starts with random input. See, symbolic just started by tracing the program and whatever conditions it got, it tried to solve it, and and so on. But this one, it starts with the random input and then accordingly it does that. So essentially, in a nutshell, what it does is it starts with the random input. Okay, let's say 22.7. Then it follows that, meaning it just puts it like normal test case. Whatever happens in the program, it observes it. We are doing both, right? Symbolic plus concrete. So we are also observing what happens. So on 22.7 for x and y respectively, whatever happens, so concrete execution takes what else branch, right? It will happen, because if we put that, we go by the code, we'll say that else case happened. So whatever the case happened, we accordingly generate a path condition for that. So this is covered, right? Like this, on this test case, this happened. So we have a path condition for that. Now whatever we get, because by observing we saw what happened. Now the condition according to that concrete input, whatever the condition is, we negate it to get the other case for which we did not have the test input. See, that is the nice case. So we start with a random input, and then we try to drive the program again in other cases, other possibilities, to other paths. So started with 22.7. Whatever happened, we negated it. We get the other case, we solve it, and so on. And whatever cannot be solved, there we'll put concrete input. That is okay. And similarly, we'll have all these three cases. Okay. So yeah, in the first case, maybe go ahead, please. Yes.
Yes, sir. In symbolic execution, you say when any condition satisfied, just like if condition we use in a code, then
Mhm.
two PC form, one for a true condition and one for
Correct.
false condition.
False. Correct.
Yes.
Very good. Yeah.
So that thing not happen in case of normal execution, sir?
No, no. In this concolic execution, what will happen is, see, in the concrete case is already giving you some path. No, some path is already there with 22.7. So
Okay.
22.7 for the okay. So for example, if I have the code open, it will be easier to understand. So we're talking about this example that was the two into y, not that one. This one, yeah. So if you say, so let's say x is 22, y is 7. So what happens? Y is 7, right? So z becomes 14. So this is 14 equal to what? This is 22, right? So 14 not 14. So z is 14. Okay, x is 22. So 14 is not equal to what is
22.
that? 22, right? Right. Thanks. So essentially, what happens is this is not right. So false. So essentially,
Yes.
according to what happened, we have the PC still. Like similar to symbolic, we have the PC. We'll have PC for both cases, but this is according to what happened. We are not like following it. Like what happened, and accordingly we generate the PC. Now to get, so this case is already covered. We need not generate input for this case, right? Because we already know what happened. Meaning we already have one xy which is doing something, no? According to, so we need not generate for that case because we already have the input for that. We will get the PC on based on that input and negate it, get the other case. So if equal to if not equal to case happened, we'll generate one for the equal to case. So once we generate for the equal to case, we'll get another condition. Now for this one also, okay, yeah, this one did not happen in the concrete case, right? Because it was false, so it did not go here. But if you negate it, you get the other case, right? So if this one becomes true. Now you have this one, so you have true and false for this one, similar to symbolic execution. Okay, so you still have the path conditions for all cases, meaning true, false for the above one, and true, true. Essentially, yeah, essentially, yeah, true, false for the above one, and this one outer one true, inner one true, and outer one true, inner one false. Three cases. So all of the path conditions are there, but the the inputs, the concrete inputs, the solutions are only for the other cases. Meaning 22.7 is already doing one case, right? So you don't need to generate it again. Meaning you're not generating
Okay.
again. That is okay. Whatever is the other case, for that we'll generate only. Okay.
Okay. Okay.
Okay, that is what happens. Now what else? Yeah, so essentially this is summary. Generate random input, execute program on random input. This we do. We see what happened. We are observing, right? So we see what happens after this, after the on the random input, what happens. Now we are going to steer the program. Because one case we saw, so we negate it. We negate it, we get the other case. right? We negate it. We use the constant solver to solve the variants, essentially, other cases apart from what happened on the random input. We want to steer away, meaning not to steer away, essentially steer to something different. That is okay. And then we generate other cases also. Repeat till all paths are explored. But then again, this might not be feasible, right? For huge number of execution possibilities. So therefore, what you do is you have some coverage criteria set. Let's say that I want to go up until depth 3, depth 4. I mean, depth 3, 4 are very small numbers, but what I'm saying is that I am only go up until depth 1000, let's say, something like that. So after that, I don't proceed and so on. So I stop. Or there's some time budget. Let's say I want to run this test case for 5 minutes and see what happens. So on. Okay,
Okay.
it could be there. What else? Yeah, there's another case. So yeah. So for example, yeah. So in this case, if you see, uh, yeah, symbolically it is difficult to uh, you know symbolically it is difficult to exercise this particular function. So we are trying to do concolic execution here. If you see, it says reaching the defective function h is difficult using a randomly generated text input. Using concolic, we can reach the arrest state in two execution steps. First we generate it. Now essentially, so if you keep generating random inputs, no, you don't know when you will hit that case when you get to abort, right? I mean, so many possibilities are there. This is just integer. It could be anything. How many times you keep generating? Like it's not possible. It's not feasible to just keep generating random integers. So therefore, both, because you're doing hybrid, no, we're doing both. So we are doing concolic. We are generating random input once. We see what happens. Again, same thing. We observe it. Whatever happened, and then we negate it to get the other case. Okay. Essentially, yeah. So x not equal to y naught, right? Because it is not equal. So this case is generated on the input, but we negate it to get the other case. Okay, and we
Okay.
generate other cases. Okay. Yeah, can colleague testing calculates the path constant. This one, yeah, not equal to happens, right? That's okay. And f of x happens on some concrete input. That's okay. Now, uh, x not equal to, yeah, because it is two, right? Okay, yeah. So if it
Yes.
goes into f, it becomes two x naught.
To
That is
max.
right. Yes, yes. So x naught equal to x naught plus 10. So if that is happening, then we go inside, right? So idea is just to get the path condition, right? Once you, like, for example, you get this, right? Then you essentially put this to a constraint solver. Constraint solver will give you a solution if one exists. If it does not exist, it might not be able to give you. But if it exists, it will give you. And then again, if you put that back, whatever you get, you are sure that you're going to follow the exact same path. Okay, it is reproducible in that way. Like you can just do the exact same thing again if you have the, I mean, this is a typical case. Even the test cases that we have, right? If you're going to run it repetitively on the same program multiple times without changing, then it is expected to be having the same way, unless there's some random logic involved there. Let's say uh, you are using the random function to generate random numbers, and based on that you're doing something, then it might differ. Okay, but if it is a fixed logic, like there's no randomness here, then it is going to be having the exact same way always. Okay, now yeah, some discussion about the constraint solver. Essentially, same thing that I mentioned. Modern constraint solver can solve complicated nonlinear functions and other things, like it can accept most of the constraints that we may see in a real world program. Okay, and many years of research spanning several papers have extended these techniques to handle pointer files and so on and so forth. We have a very good solver actually. That's what it is saying. Okay, some tools are given here. So we have for Java, .NET, and other such languages. Okay, so this concludes the discussion on symbolic. I think, yeah, actually symbolic and concolic shared the slide deck. We have Dart. Dart is the algorithm. So this is the approach. Like this is the technique, right? Like this is a theoretical technique. Like we're mentioning that this we can do. We have discussed the technique. Now there is also one implementation of this technique. Implementation in terms of the algorithm. Like exactly doing. How do we do that? Like symbolic testing is one thing, or rather Dart is concolic actually. So that is one implementation of concolic testing. Like for concolic testing, you may have several algorithms. One is called Dart. Okay, so this is just a discussion on the Dart algorithm itself, like how it works. Okay, so it may be that I'm not sure. I don't think we'll have questions on this specifically, but idea is that if you can go through that, no, essentially same thing. The technique is same. We are still doing concolic testing. Okay, so we know what is right. Just that Dart uses some specific notation and so on. So you have to be careful about that. Like for example, we have comma no here, so x naught not equal to y naught, comma 2 into x naught equal to x naught plus 10. So comma is assumed to be and, right? So if you are having this kind of a set, it says that both conditions should be true. That's how you represent constraints. So this is the only distinction, that is the technique is the same essentially. Okay. Now we have the solution. Okay, and so on. Record it, keep it like that. Yeah, one thing that you have to remember with respect to Dart is remember the symbolic names that we were giving to variables, like this one, x naught equal to y naught, and so this one we were giving, right? This mapping, like for the actual x variable, the mapping, the symbolic mapping is x naught. So in Dart, this is handled by the memory locations essentially. The symbolic variables are identified by their addresses in the memory. Okay, remember that in the program, in any program, every variable that is created is mapped to some memory address. If you know what that is, essentially. For those of you who are going to take operating systems course, maybe going forward, there's an elective on operating systems. So there, you might want to like you would be learning about these things. Other might be that if you take the C course also, C programming in C, there also we discuss this. But essentially, idea is that the variables that are there in the program, no, all of them are associated by some addresses or references that are there. Yeah, you've done Java, no? So memory references, you maybe know about that, right? Essentially, we have the
Yes,
references
sir.
to the variables. Yeah, exactly. So in that, the variables are identified by their addresses. Instead of saying something like x naught or y naught like this, we already have an address. So we correspond, like we correspond x to that address in the symbolic representation. Essentially, that's what it is. Okay. So and yeah, some notation again. So essentially, it says that not it's the same thing we are borrowing from. We are borrowing some things from the logic only, like the logic notation. So not of, if e is a condition, then not e is, like if e is true, then not e is false, and so on. Okay. And similarly, you have a pointer dereference also. If you know C, you might know what this is essentially. Yeah, pointers are in C, right? So if you go through the C course, you may understand that. But idea is that it is, I mean, there's nothing much to remember here. Just that you might want to remember how it works, like the data algorithm, which is actually overlapping with concolic testing, because this is an implementation of concolic testing only, right? So it will be have work in the same way, but there's some data specific details that are there, but it is okay. Maybe you can go through that. The only thing that you might want to remember is this.
Excuse me, sir.
Just a second, please. Let me just yeah, this part you have to remember that it is addressed by a memory location. Other than that is just a detailed discussion of how the data algorithm exactly works, like what it is doing and so on. So, okay, so this is okay. Maybe you can just go through that. It's not very important as regards the programming. I mean, as regards the exam, that is. You can. This is like discussing in detail what exactly is happening. Okay, but this is, in essence, it is just doing some concolic testing. Okay. This is okay. Yeah. Yeah, I think this is okay.
So this Dart part not important for exam, sir.
No, dot, you just have to remember some notation. Okay, notation meaning remember this. I'll tell you exactly this one. Yeah, one thing is that it is
Comma
memory addresses, and the comma representation. This one.
at place of
The
and using comma.
yeah, this one. And yeah, in place of and you have comma, and yeah,
Um,
this dot is multiplication. That is okay. What
yes,
else?
yes.
Yeah, some of them you may just see here. No, this one. So most of it, in two is multiplication. We know that. Yeah, this is a constant. That is okay. This comparison. This not is negation. We know already. Only thing is pointer dereference, which is also using a star, but it is okay. I mean, you may skip that. It's fine because this is part of the C programming language. We may not ask. Okay, this is just the notation that you might need to remember. Other than that, again, concolic testing only. Like this part, we already seen that, right? So essentially, like how it works. The generate random input, execute program and input. That is what Dart is doing also. It's just that it is specific, like what exactly it is doing with the code and everything. But the idea is same. Generate random input, execute program on random input, collect the symbolic path constraints. Like this is just the theory part, right? Collect. But how do we do that in program? Right. So essentially that is what is being discussed in Dart. Okay, so collect symbolic path constraint, and then again you negate it. How do you get the other case? Always remember that. Don't get confused. Okay, so if you have one PC, the other case can only be we can only get it using by negation. So we negate it. Okay, if it is equal to, we make it not equal to. If it is greater than, we make it less than equal to. If it is less than, then you make it greater than equal to, and so on. The other case, the negation. Okay, that's the only way you get the other possibility. Okay, so yeah, go ahead, Balakishan. I think wanted to mention something in the
Yeah.
chat.
I have a doubt in the practice assignment of week 7.
Okay, just let
Can I
me.
show you?
I can. Oh, you can do that, right? Yeah, sure, sure. Go ahead,
Is that the
please.
screen? Okay.
Yeah, week 7 deadline is not over yet, right? I think, but
I
practice
said
and we can discuss.
practice assignment,
Uh,
not graded.
practice we can discuss. Yeah, practice we can discuss. Yes.
You're able to see now?
Yeah, yeah. Go ahead. Yes.
Okay. So in question number 6,
Mm-hmm.
uh, it's actually swaps with values of values x and y
Mm-hmm.
only if x is less than y, right? In this question.
No, no, I have to go through that. I'll understand. So essentially, okay, x, y. If x is greater than y, okay, then you go inside and then you swap. Huh? Yeah, yeah. Okay, so if it is less than, you're not going to go inside, right? That's correct.
It should be actually really only if x is less than y, right?
Mm, x is greater than y, you are saying, I think. You
X is
mean
greater
x is
than y.
greater than? Yeah, if x is greater than y, then no, I'm talking about line number 2. If x is greater than y, then only you go inside, right?
Okay, yeah, yeah, yeah.
So is that what you're saying, or is that something else? I'm not sure.
Yeah, that only, yeah.
Yeah,
And my
yeah. So that.
second
Okay, go ahead. Yeah.
and the second doubt is how many nodes will there be in the symbolic execution tree of this code fragment? 8 nodes, but how is it 8 nodes?
Yeah, yeah. See, thing is, yeah, with respect to symbolic execution tree, I just want to mention one thing. We've given in practice. Idea is that there are at least, I mean, there may be more ways, but there are at least two ways of drawing symbolic execution trees for the same code, okay, and which may have
Okay,
differing number of nodes. The number of nodes in the symbolic execution tree for the same program may vary depending on the convention you're following, okay. So
okay,
we had also discussed this with the professor long ago, actually, long ago. So
okay,
she also suggested that there are two possible ways, and sometimes the students, were getting confused as to like how many number of nodes are there. So we then decided not to ask the this question of this has been practice assignment. That's okay. Like you can try it or draw it and try it. But in the
okay,
exam and the quizzes and the graded assignments, we will not be asking about the number of nodes because they can differ, okay,
okay.
for the same code. Okay, so this will not
Right.
ask. Thing is that sometimes we merge it. Like sometimes we merge two statements, sometimes we don't do that. Like there are different conventions to do that essentially. So therefore, it varies the number of nodes. So therefore, we are not going to ask it. Uh, yeah, I think that's the part.
And
Uh,
just the last doubt.
mhm, mhm.
Um, yeah, what will be the path? The question number 9. What will be the path
Mhm.
constraint to reach line 6? Should it be to
Mhm.
reach line 7 instead of to reach line 6?
Can you go up in the code, please? And no, no, it is asking about line 6 only. You're asking about assert false. Yeah, I mean essentially, if you yeah, okay, assume that we're talking about line 7. It's the same thing, no? Even if you reach, see, even reaching line 6 is to reach line 6, you have some conditions, right? Above that. So to reach
Yeah,
line 6, you have to have, you know what you have to have? Mm, Okay, so x is being flipped. So assume that x is greater than y, then x and y are switched. So now y is greater than x. So therefore, what will happen is, yeah, if x is greater than y, meaning y is small. Now I am swapping, right? So x was greater. Now I swapped. So now x is no longer greater. So if that happens, then we are not going to go inside anyway. Okay, yeah, yeah. I think they are asking about line number 7 only.
yeah. Line number 7. Yeah.
Mm-hmm.
I was wondering whether it should be like to reach line number 7 instead of line number 6.
Yeah, line number 7. Essentially, we will put the call. We'll say how do we reach assert false or whatever abort call or some call is there, no method call. We'll name that
Okay.
method. We'll say how to reach that, or it will be clearly given which line it is. Okay. This case, I
Okay.
think is mhm. Okay.
Yeah. Okay.
All right. All right. Anything
Sir,
else?
I also
Yeah. Go
have a
ahead.
doubt on the
Mhm.
same question, but it's good if you draw one path constraint for the same question, this code.
This one. Okay. Okay. Sure. Let me
Yes.
see if I can. Yeah. Just give me one moment. I'll share the other screen wherein I can write also. Okay.
Okay.
Yeah. Yeah. Can you still hear me? Just wanted to confirm. Maybe.
Yes, sir.
Okay. Okay. Sure. Sure. Sometimes it. Okay. Still fine, right? Okay. Fine. So yeah. Now I'm going to write that. Let me just also open that. Practice assignment 7. Just a second. This portal is opening up. Can you tell me the code also? Like, is it possible? Because it's not open with me. So you have X and Y, right? Let me see. Week 7. Hmm.
Sir,
Yeah,
in
thanks.
chat, I placed.
Okay, okay. Thanks so much. We have. Okay, I'll try to write here. Okay, X comma Y. This is one part, and then you have X if X greater than Y, then X is equal to X plus Y. Okay, and Y equal to X minus Y. Yeah, this is a swap. Okay. Now X is equal to X minus Y again. Okay, and then if the nested if X minus Y greater than 0, which we can rewrite, no? Then assert, sorry,
Pause.
yeah, assert false. This is the one we have. This is kind of close, and the outer one also. I think that suffices, right? Okay. Now, where you want to go? Like, what is the path constraint that you're asking about?
So I have a doubt how we represent that code in using node, first thing, and second, how we find the path constraint for that code.
How do we represent using node? Okay, so one convention. You are asking about symbolic execution tree, right? The first question. I'll come
Yes,
to the
yes.
second question. Okay, so
Okay.
symbolic execution tree. One way to do that is you consider each statement as one node, right? The simplest way, and the other, the other ways also, right? But what you do essentially is like this. So essentially, yeah. So let me see. Now we have this. Okay, on the symbolic execution tree, you'll have that. If yeah, that looks like CFG only, right? Yeah, just a second. Let me quickly see if we have both the ways. Just a second, please. Uh, okay, so yeah, so we have a tree like this. So essentially, the first thing is you have something like this. This is one of the ways I'm drawing. Okay, the other way also which causes confusion sometimes, but this is one of the way I'm just drawing it. So essentially, so what do you do first time? You assign it some symbolic values, right? So let's say x I'm assigning to x naught, right? Y I'm assigning to y naught. Rather the other way around. Y naught is yeah, x naught y naught like this. Now, so what happens is one case is that so there are two now once you do so this first node corresponds to this. Okay, let me just draw also so that you understand what is what. So this part is this. So actually not this. You have a above that you are accepting also no some method is there with which you accept it. Oh, it's not the full code, but assume that it is coming from some method. So assume okay, better would be to do something like this. So let's say
3.13.
there's a void check here. Okay, I'm checking x y like this. Okay, now remove this part. Okay, so instead of putting yeah, this also works. Like essentially, if we start with that, but assume that I'm taking input, right? So instead of taking it in the like initializing in this one, I say because you don't know what is going to be the symbolic input, right? So better to consider this. Okay, this part. So I get it. I at that moment I itself I assign it. Okay, I have a closing here also. Fine. Now, oh, I think that was anyway. So now you continue like this. Just a second. So now there are so this part is done. Now what is the next line? Next line is this, right? So you draw two edges, like branching statement. So you have one case
Yes.
similar to your CFG only, right? So you have the other case. Right. So in one case, what could happen is that x is greater than y means what? X naught is
अब कुछ काम कर रही होते तब भी ये डिस्ट्रिक्ट
greater than this is symbolic one. Why not?
Why not?
Yeah. The other case would be what? You know that
X
else
not.
case, no?
Yes.
Less than equal to. Why
Equal
not?
to why not?
Yeah, you cannot miss out on the equal to, right? If you do so, then there'll be three cases. Yeah,
Yes.
the strictly other case would be less than equal to. Okay.
सबसे पहले
Now
तो
this is the case. Now,
लीज
so what do you do in both cases? If this happens, mm, yeah, if this happens, then you do what? Just a second.
Update variables.
Update the variables. So essentially, no, I'm talking about the other case. So if this case happens,
ये चला रहे
Program exit.
yeah, it'll be program exit, but what is the corresponding you give some input which will satisfy that. So let's say x is equal to 3, uh, right, and y equal to 7, for example, right? So essentially, it is similar to what we have seen in the slide also, no? So if this input is there, so this case will be
Yes.
executed, right? That is the other case is update. So you have this the other case. The other case is that x gets updated to x naught
अरे ये सारी
Plus y
सेटिंग
naught.
ने
plus,
टीम भी चेंज
yes,
कर दिया
very good.
हाँ वो भी
And
T3-2025
y
है
gets updated to
X naught
sorry,
minus y
what?
naught.
इसने बदली है यार इसने क्या स्ट्रक्चर
Y
रखा
gets
है
updated to x naught minus y naught, huh?
Yes.
So x naught minus y naught happens here, huh? Okay, and then so idea is that okay. See, yeah, that's where the confusion comes in. Sometimes what happens is therefore the symbolic execution tree also differs. This portion, no, I'll just highlight it. This portion, no, this is what these three lines. This is what we call a basic block. Okay, if you can read about that in the slide also. So basic blocks sometimes we combine it into one thing only. So this x plus, so the net result we'll write down essentially. X plus y happens, and then x minus y happens, and x. So we swap it essentially. So that part only we will write down. We will not write down it separately, but in this case I'll just write down separately so that we understand clearly what is happening. Okay, now so we have y. Yeah, y getting assigned to this one. Uh, yes.
ये वाली
So case is okay. X is getting assigned to x naught plus y naught. Y is getting assigned to x naught minus y naught. Okay. Now, yeah, now the other case is x is getting assigned to this one. Okay. So this case is happening. Then, okay, consider that it may be combined also. Okay, in the same branch, but just to represent, I'm trying this. Okay. So now you have the last one, which is x going to.
X naught
This
minus
is
y
x.
naught.
Yeah. So no, this will be what x naught plus y naught minus. So essentially, you have to write it like this. If you want to write it in the expanded form,
वो जो अभी
it
कमांड
will be
आती है
something like x naught plus y naught minus uh, y naught. This is x naught minus y naught. Yeah, x naught plus y naught minus x naught. No, no, just a second. I think I'm missing something. Just this.
तो डेटाबेस इशू है
Oh no, 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 no. I think I made a mistake there. Just a second. This one is slightly different. Actually, for the y expression that I've written is wrong. This one is not this. See, remember what is happening. You have to be careful with the flow. The x is what is provided. No, this one. Uh, this above one. We'll use a different color maybe. This one, right? This is what is provided, and I check with what is provided. So this for the first part is okay. Now the moment you hit this line, right? Now in y, this x is not that x. Okay. So this x is actually x plus y minus y. So essentially, if you were to expand it out somewhere, this is what this is x plus y minus y. Okay, x plus y minus y, because at this moment x is not x naught. That is not the, you see. I mean, that is not the x naught that
I
we're talking.
understand, sir.
Yeah. So essentially, this will become what, x naught plus y naught. This is x minus y. So
Minus y naught.
yeah, that's how you swap. Now this one is different. Uh, just a second. Sorry about the. Okay, so this one is done. Now x naught is the last part, right? This one. So at that moment it is x naught plus y naught. No, no, just a second. So this is the same thing. Okay, now, okay. So the next part y is changed. Okay, now y is this y. So you will have x naught plus y naught minus x naught plus y naught minus y naught. Okay. So this is slightly convoluted. Just a second. I will just. It is good to draw the path conditions also, because you just straight away take it from there if you want to. You know, it's good to see it that way. I'll just make it bigger. So essentially, what is happening with y, here, rather with x is being assigned x minus y at that moment, right? So at that moment, it will be x naught plus y naught minus x
Minus.
naught
Minus y
plus
naught.
x naught plus y naught minus y naught. Yes, that's correct. So essentially minus y naught. So essentially these two gets cancelled out and you get minus. That's how it is swapped also. Okay, so this part is done. Now
Uh, so what the value of y?
value of y at this moment is this one.
Oh,
So this is that y that I am replacing. The
okay.
entire thing. So this is your x and this is your y. Okay, so x is x minus y, no? So at that moment different. Okay. So this is okay. Now that's how you have to follow. Okay, now another condition after this. So if this happens, yeah, after the swap, this is after the swap, we're going to have a condition, right? So assume that, sorry, uh, first case, second case. Okay. So now what is the condition check? Condition check is x minus y greater than 0, which is, so this we can rewrite, no? This one. This we can also say that x greater than y, because I'm just, this y I am just moving it to the right hand side, you see?
Yes, yes.
So yeah, okay. So essentially, just make it shorter. So x, so what is x at that moment? So essentially x naught plus y naught. This is x, right? Yeah, no,
X
just a
naught.
second. I just simplify it. So this one goes, that one goes. You have x as y naught. Essentially, at that moment, x is y naught and y is x naught. Right? This gets cancelled out. These two. Okay, so
Yes.
y is x naught and this is basically swapped. Now I'm checking for what? I'm checking for x greater than y, which is y not greater than x naught, right? That's what the swap happens. Y not greater than x naught, not x not greater than y naught. Okay, because it got switched. So even though we are checking for x minus y, we are actually checking for y naught. This is y naught at this moment, and this is x naught. Okay, so y not greater than x naught rather than x not greater than y naught. Okay, this is a change here. So y not greater than x naught, and the other case would be y naught less than equal to
X naught.
x naught. Very good. Okay. So now, so if it is greater than, then what happens? Meaning y not greater than x naught, then this happens. Assert happens here. Okay. If that is not the case, then I just exit the program. So this is call it exit, whatever. And even after the assert, I think yeah, assume that after assert it is implicitly ending. I mean, otherwise you could have end here also. But okay, so this is how it looks like. Is that okay?
Okay, so possible path constraint in this graph, sir. Oh, I think two.
Sorry, I didn't get you, Shoni. Can you repeat that, please? I think I missed the last part. What was that? What is
So
the
how
question again?
many
Mhm.
path constraint? I
Path
don't know. I'm
constraints.
true or wrong. Yes, yes,
Oh
yes.
yeah. How many path? Yeah, exactly. So how many path constraints are there? We'll see. So one path constraint is this. Uh, See, path constraint can only be at the decision node. Okay, this is for sure. This is fixed.
Okay.
It cannot be anywhere
Mm.
else. Okay, so we are talking about only if conditions. I mean, it is better to see from the code. I mean, you can see from here also. Thing is that you have this if condition, that if condition, right? So two. So in this
Yes.
if condition, what could happen? Two possibilities, right? So you have one
Yes.
case which is x greater than y. The other case
And
is x less than equal
less
to.
than equal to y.
This is for the first if. The second if you have. So just switch. I'm just switching it. Okay. I'm saying y greater than, because I know it got swapped right at that moment. So y greater than x, and the other case is y less than equal to x. So four path conditions, right?
Okay.
Yeah, but if uh, just a second, let me think about it. So mm, yeah, actually, what happens is, see, for this one, for the first one, if it is false, meaning if this is this condition, right? Then after that
Yes.
it ends. After that it ends because it is
Yes.
false. It ends, right? If
Yes.
it is true, If it is true, then you have
Again, two
yeah,
condition.
you have two conditions. Yeah, then you have this and then you have that. Right. So
Yes.
essentially, yeah, I mean, how many? No, no, actually, yeah. So essentially, this part is one, two, and this is three. Three part
Three.
conditions. Okay.
Yes, yes.
Similar to the other one, right? We have seen that in the other that program. Right. On the slide, also similar thing happened, right? Because
Yes,
see,
yes.
if this is true, then only you go and check this one. So this is like together. Okay.
Yes,
So
sir.
that is why it is three. Three path conditions are here, and this is the number of nodes. Please don't go into that, okay? Because the number of nodes may differ
Okay,
and so
okay.
on. Okay.
Okay.
The other one is yeah. What else? That okay? Anything else on this?
No, no. Everything clear.
Clear? Okay. Okay.
Yes.
Uh, all right. Okay. So then for today, I think we may close. Um,
So quiz to syllabus is from week 5 to week 8.
week one to week eight.
Oh, week
We have,
1.
yeah. Week one questions will be there. Yes.
Okay.
Yeah. So you have to go through the. I mean, see, less number of questions will be there. Emphasis from week 5 to week 8 only. Like weightage, not weightage, but more number of questions are expected to be from there. But again, I cannot guarantee anything. Because the thing is that it's better you go through the, especially the the coverage, prime path, edge pair, and edge coverage and all that. Right? From the first 4 weeks. Okay. Do you know anyway, right? Do you paths,
Yes.
all depths, all users? Yeah. So that's what we're going to just ask problems on that, and some theoretical questions may be there. And then from week 5 to 8, so you have coverage RACC, sorry, RACC, CACC, GACC, GICC, and RICC. These five.
Okay.
What else? I think, yeah, that suffices. Yeah, symbolic execution, you'll have, again, remember for the loop, okay? Don't get confused with the loop, interval, and so on, okay? Maybe you can practice with that. That question may be there. All right. Okay. So, yeah, with this, we'll close. Thank you so much for
Okay.
being here.
Thank you,
Thank you,
sir.
sir.
Thank you so much.